Hello. In this video, we're going to look at the chain rule, which is section 3.4 in your textbook. Now, hopefully you've already tried the problem of e to the power of 2x finding the derivative. But if you haven't, I encourage you to pause the video and really see if you can give this an effort. See if you can find out the derivative of e to the 2x. If you're still struggling, I could even help you out. You could even consider e to the 2x maybe as e to the x all squared using our power rules, which is e to the x times e to the x. Perhaps you could even use the product rule without even using the definition of a limit. But hopefully you've given it some type of attempt. And let's go ahead and see if we can find the derivative. Again, we thought it might be e to the 2x, but perhaps there is some other 2 going on in this limit and in this derivative. Well, let's take a look. The limit as h approaches 0 of e to the 2x plus h minus e to the 2x over h. So we have to expand that as e to the 2x plus 2h minus e to the 2x over h. And again, our exponent rules are definitely our friend here. We can write this as e to the 2x, e to the 2h minus e to the 2x. Remember, when you are having the same base, you add the powers. So if you were adding the powers, you could split it up as multiplication with the same base. Now there's an e to the 2x in common, so we're going to factor that out. Limit h approaches 0 of e to the 2x, e to the 2h minus 1 over h. Again, the e to the 2x can come all the way out of the limit because it's just a constant with respect to h. But here we've got to do a little bit of work because e to the 2h minus 1 over h, well, it's not entirely clear what happens to this. You could definitely use your definition of e, and that would be one way of using it. E is 1 plus h to the 1 over h. That would work. But I'm going to show you another method here that I think is kind of fun. We're going to take e to the 2h. And just like I showed up top, e to the 2h is equal to e to the h squared, because power to a power means multiplication, which means e to the 2h minus 1 is equal to e to the h squared minus 1, which factors as a difference of squares, e to the h minus 1 and e to the h plus 1. If you don't believe me, well, we multiply it out. E to the h times e to the h is going to be e to the h squared. Then e to the h times 1 is e to the h. E to the h times minus 1 is negative e to the h, those cancel out. And we get a negative 1 in the end. So this actually factors beautifully as a difference of squares. E to the h minus 1, e to the h plus 1. Well, if we were to plug in the h as 0, e to the h plus 1 is going to be e to the 0 plus 1. 1 plus 1 is 2. So this portion is just a 2 and this has no issue. This is the portion over here that's giving me the problem. And we remember our special limit. So we have e to the 2x times, and we could write it like this, limit h approaches 0, e to the h minus 1 over h times limit h approaches 0, e to the h plus 1. Now remember, that first limit is our special limit and it equals 1. So we have e to the 2x times 1 times e to the 0 plus 1, which again we argued above was equal to 2. So this is 1 plus 1, which is 2. And so our final answer is 2 e to the 2x. Now, again, I alluded to a bit of a shortcut above. So I'm going to show you the same argument with the product rule. E to the 2x is e to the x squared, which means e to the x times e to the x. So when we do the derivative of e to the x times e to the x, we use the product rule. Derivative of the first, leave the second alone, plus leave the first alone, derivative of the second. It's hard to see that you're actually doing derivatives because the derivative of e to the x is just e to the x, but here you go. We've got 2 e to the x, and x plus x, of course, is 2x using exponent rules. So this is the same either way. Whether you use a little bit of product rule or whether you use the derivative definition with the limit, either way you get 2 e to the 2x. And so back here, our guess of e to the 2x was slightly correct, but we should really put down the correct answer here. It's 2 e to the 2x. Now, the fact that we get an e to the 2x kind of makes sense because the derivative of e to the x is e to the x, but what's this 2 doing here? Why is there this 2? Does the chain rule have some sort of 2 rule going on? Well, let's see if we could do this with another function. What if we had sine of 2x? What do you think the derivative would be? Well, maybe you would predict maybe cos, because the derivative of sine is cos. Do we think there might be an x inside, or is there maybe a 2x inside? Is there another 2 outside in front? Potentially. Potentially. Well, let's see if we could prove this. We know that sine of 2x has an identity. It's 2 sine x cos x. And now we're just back to the pure, if you notice here, just a pure x, which we can use our regular rules on and, of course, our product rule. So the derivative of 2 sine x cos x will be, derivative of the first is cos x, leave the second alone, plus, leave the first alone, derivative of the second is negative sine x. So we get 2 cos squared x minus 2 sine squared x. Well, there's a 2 in common there, so you could factor that out as cos squared x minus sine squared x. And, well, we have an identity for this. If you look at your identity sheet, cos squared x minus sine squared x is actually equal to cos 2x. And so this up here is correct. This is the correct derivative. So what's going on here? What in the world is happening? We have this kind of double derivative at the same time, maybe, maybe not. The derivative of sine is cos, so that makes sense. I guess the 2x just has to be rewritten, but why is this extra 2 here? It's almost like there's a second portion to the derivative, but not quite. If you were to think about it, what would be the derivative maybe of cos 2x? Do we have a prediction on what that might be? Or maybe the derivative of e to the 3x. What would that potentially be? What's going on with these questions? And in particular, if I was to write something like this, what would be the derivative of e to the 2x plus 5? Now again, I encourage you, pause the video and think about this. Make some predictions. What do you think these derivatives would be? Hopefully you've had some time to think about it. I'll give you the answer for this one, and you could prove these just by using some identities. The derivative of cos of 2x is going to be negative 2 sine 2x. The derivative of e to the 3x is going to be 3 e to the 3x. And the derivative of e to the 2x plus 5 is going to be 2 e to the 2x plus 5. Now maybe you're starting to see the connection. I'll help show you if you're not. The 2 inside here is, well, going along for the ride. There's a 2x, a 2x, a 3x, a 3x, a 2x plus 5, a 2x plus 5. But the number in front, the 3, well, it's obviously coming from the 3x, and the 2 is coming from the 2x. But why isn't the 5 coming down to be with the 2? Well, think about it from a calculus perspective. What is the derivative of 2x? Oh, well, that's 2. What's the derivative of 3x? That's 3. What's the derivative of 2x plus 5? Well, the 5 is a constant, and so the derivative there doesn't matter because the derivative of 5 is 0. But the derivative of 2x is still 2. That's why we just get a 2 in front here. In fact, what you can think of is that we have what's called function composition. If you had a function fx as, let's say, e to the x, and gx as maybe 2x plus 5, if you were to calculate f of g of x, you would get, well, f of 2x plus 5, which means everywhere you see x, you replace it with 2x plus 5. So the function e to the 2x plus 5 is really two functions. It's an e function, and it's a 2x plus 5 function that have been composed, that have been function composed with one another. So when we do the derivative, there's this aspect where both of these need to have a derivative done to them. But they happen in a certain way, and we'll look at this more as we go through some examples. So go ahead and practice this rule on the following questions. If you're not sure how the rule is working still, feel free to just make a prediction, and then I'll go through the answers in a moment. So pause the video and give it a try. All right, so let's do the first one. The derivative of cos is minus sine. The 2x goes along for a ride, and of course we have an extra 2. Now you can put that 2 in front. I'm just going to put it at the end just for simplicity's sake. Now here, you can think of this sort of like a giant x to the power of 5. So if I have x to the power of 5, well, the derivative of x to the 5 is 5x to the 4. In this case, I will now have 2x plus 7 to the power of 4 times 2. All right, what's the derivative of tan? We remember that one is secant squared. And then we get our extra 2. Cotan is negative cosecant squared, 2x. And we get our extra 2. For this one, again, we have to write this as a root, or as a power, I should say. So we get 1/2, 2x plus 3 to the negative 1/2 times 2. Now, if you notice here, we could simplify as, well, there's a 2 on the top, a 2 on the bottom, and this could be written as root 2x plus 3. You could actually cancel these 2's, and you'd be left with 1 over root 2x plus 3. If you remember this from an earlier video, we actually had this exact question, and we wondered why there wasn't a 2 with it, because on the other ones, we had this root give us a 1/2. But now for some reason when we do the derivative, the 1/2 disappeared. Well, the reason was because there was an extra 2 on top and an extra 2 on the bottom, and they canceled out. That's why there was no 1/2 when we had done this, just using the limit. Now one more question here. Secant will be secant 2x tan 2x times 2. So the rule that's going on here, just to help clarify for you, is that if you have two functions, f of g of x, and you're trying to do the derivative, well, it appears like, and you can see very clearly on, for example, the function at the very top, cos 2x. It appears like you take the derivative of cos, which is negative sine. In this case, you take the derivative of f, which would be f prime. But the inside portion, the 2x, remains as a 2x. So you can think of literally just leaving the gx as a gx. Then we have to multiply by the derivative of that inside portion, the derivative of 2x, which we would write as g prime of x. This right here that we have, this is the chain rule. We'll prove it in the next video, and we'll explain it in more detail. But for right now, we're just going to go ahead and practice it on a few more questions. So let's practice this rule on the following questions. Go ahead and pause the video and give them a try. All right, so here we have sine. We know the derivative of sine is cos. And the inside portion, the inside function, just gets rewritten. Then we multiply by 5. For cos, we get negative sine of 6x plus 2. And then we multiply by a 6. Again, the derivative of 6x plus 2 is just 6. The 2 just kind of disappears. Here we have 4 root 3x plus 6 to the power of 3. Again, you want to think about this like a gigantic x to the power of 4. And then we have to multiply by, well, the derivative of the inside portion is just actually a root 3. Kind of weird there. Here we're going to get secant squared pi x minus 4. And the derivative of that inside portion is actually pi. Finally, for the last one, we get negative cosecant squared of ex plus 2. And the derivative of that is just the letter e. Again, those are constants. They're not really functions because there's not any x. It's not e to the x, it's just e times x. So in this case, the e is kind of representing just the number like 2.71 if you want in front of the x. Now to extend our knowledge a little bit, I want us to think about functions like this. What if we had sine of x squared, or sine of e to the x, or e to the sine x? What would be these derivatives? Again, pause the video and give these ones a prediction. All right, so for sine of x squared, we would do the derivative of sine, which is cos. And then we would do the derivative of x squared, which is 2x. For sine of e to the x, we would do the derivative of sine, which is cos. But again, we rewrite that inside function first. Then we multiply by the derivative of e to the x, which is e to the x. And this last one is especially tricky. The derivative of e to the x is e to the x. So we get e to the sine x because that's just doing the derivative, but of course e to the x is always e to the x, so it just gets rewritten. And then we multiply by the inside derivative. The derivative of sine x is cos x. In the next video, we're going to go ahead and prove the chain rule, and we're going to look at some more in-depth examples of how this is used on certain functions. Hopefully you enjoyed this introduction to the chain rule, and as always, thanks for watching.